Okay. Okay. Test, test. Okay, I think we're going to go ahead and get started here tonight. We're down to the final two sustainable energy, sustainable homes seminars, April and March, or March and April. And we've got solar hot water tonight and solar photovoltaics in April. So we've kind of moved through a progression of cost effectiveness, general concepts, to case study, to design concepts, to renewable energy. And if you're thinking about home improvements, it's always good to start with energy efficiency first, and then renewable energies afterwards. So you've got your meat and potatoes, and then your dessert for afterward. So I'll do a little bit of housekeeping. My name is Chris Wilson. I'm with the U.S. Green Building Council, and we're hosting the Sustainable Energy, Sustainable Home seminar series. If you found us through the Community Learns, the Boise Community Learns program, you're paid up and you're all signed in. You're signed in through the electronic system, but we do have a sign-in sheet like everybody to sign. So if you haven't done that, make sure you find that. And we've got our payment box if you're not a sponsor or not a season pass holder. So also, we're in the IDL, the Integrated Design Lab of the University of Idaho. They're hosting us. That's the space we're in. And they've got a nice high-tech lab on this side of the room, so we want to stay clear of that. If you need to use the restroom, you can head all the way down the hall to my right. It's a long hallway, but there's a door through there, and you'll get to the bathrooms on the end. I'll need to go prop the door open as soon as I'm done doing the intro because they put a key code on it, so we don't want to have you locked out, but I'll go take care of that. So again, tonight's tonight's topic is solar hot water, days of our hot water, and Stephen Howe with Renewable Energy Solution is going to be telling us an intro to solar hot water. So the basic concept of how you use the sun's energy to heat water and provide hot water for your home's domestic hot water heating uses, maybe even heating the home with that solar heat. Our series, welcome, is brought to us by some faithful sponsors. I'll list in alphabetical order: A1 Heating and Air, Better Homes and Gardens, Avant Properties, the Boise Weekly, Building Energy Inc., Earthcraft Construction, Franklin Building Supply, Flying Cowboys Design and Remodeling, Gravitas Design. Green Remodeling is our title sponsor, and they started the series 7 or 8 years ago, and I've been involved ever since. Idaho Power is our statewide sponsor. Johnson Brothers, Windows and Doors, Osprey Building Performance, Renewable Energy Solutions, Solar Cascade, the University of Idaho, who's giving us the space here at the Integrated Design Lab, and U.S. Green Building Council Idaho chapter, who I'm representing. So that moves us into Stephen's topic tonight, the introduction to solar hot water, and I'll go ahead and hand it over to Stephen.
Can you hear me? Can you hear me?
Yeah, you're good.
Test? Yeah? Okay, so this is an introduction to solar thermal systems, and we're going to be talking about solar hot water, both used for domestic hot water uses and also for space heating. So you see the blue green John King. It was for space heating. It had 4 of these big 4x10 flat panels, and some time ago now. It gives you some idea of what sort of is involved to mount. Or coal. Okay, a little off in here. Right. Nope. So, what's solar hot water all about? Well, it adds renewable energy conservation. That's really what's going on. So, we've already had quite a bit of discussion and seminars and ways of conserving energy. Now we're in the process of making the transition to creating energy. So we're using the house as an energy source, and we're heating hot water with it. It's a transformation of energy production from fossil fuels to low carbon renewable source. It's reducing the environmental cost of energy production. Almost any means of producing energy comes with environmental damage. It's an attempt to mitigate that environmental damage. And it's reducing the environmental cost of energy production. It produces renewable energy immediately. You don't have to wait. Once you've installed it, you're up and producing energy. The primary, provide shelter, keep the elements out, there's architectural functions of it. But now what we have is a function that says part of the reason for a roof is to create energy, not only for the house, but later on for the car. So we're changing the function of what the roof, we're expecting from the roof, or actually from the envelope. And we're using energy. So we're using energy to produce energy in renewable form. So it's not like we're not using energy to produce the copper and the glass and the pumps and all that sort of stuff. Energy is being used there. So once you're up and running, then the function of energy usage is then to enable the production of energy. How are we doing? Oh, you can't hear anything. Okay. So what are the attributes of solar hot water systems? About 15% of the household energy is used to heat water. So the total budget for energy use, household water is pretty good size. As I said before, it's clean, renewable, sustainable energy. It reduces the CO2 production by about a metric ton per year. a hybrid system where energy is used in combination with conventional energy backup. It's very difficult to design solar hot water systems so that they and they alone produce all the solar hot water. And so you don't do that for design goals. Shoot for a system life of about 30 years. It doesn't have to, don't have to replace parts, but you will have to replace some parts. Water heaters don't last for 30 years. It's a wonderful solar resource on the tropical side of it. We have a great time for solar. We have the winter inversion in December and January, and those months up there. But the rest of the year is just for the production of solar hot water. And then there's states in the federal and summer as well. Okay, here's a system diagram of a typical single tank active closed loop system. Now there's a lot of different ways of implementing solar hot water. This is one of them. And this particular one is a closed loop glycol system. And glycol is used because water will freeze. There's a guy, Carl Simpson, who's got a different system in which he uses water in there. And then he uses a pump to keep it circulating. So there's other ways. So the drain back system of the water comes back into the tank and it doesn't use that. But this particular system uses glycol. And because it's using food grade propylene glycol, it needs to go through a heat exchanger. So the water in the tank is with enough hot water. And the water in this glycol is a mixture of 50% propylene glycol. When the temperature shows a different kind of heat exchanger. Okay, here we have two collectors.
I think it would have to be off.
Here there's a commercial unit, which is an appliance. And in this appliance is the pump, the heat exchanger, the differential controller, all that sort of thing. And in this kind of system, the heat exchanger isn't in this tank. This is simply a storage tank. And then this is a conventional water heater, either natural gas or electric. So the way this works is that cold water comes in into the solar hot water tank, and this is heated to as high temperature as it can be. And then it goes into the natural gas water heater after it goes to this mixing valve. And then the natural gas water heater boosts it if it's required. So in the wintertime, you don't get very much boost out of the solar. Maybe it'll go to 90 degrees, and then this one takes the water from 90 degrees to 120. In the summertime, the water coming into here is already at 120 through this mixing valve. And so this doesn't turn on at all. This is, you can almost unplug this. And I do all summer. This is the kind of system I've got in my house. So this system really works very well in terms of it's more efficient because you're using this big volume as solar storage and using a smaller volume to keep, to just boost what's going on. But the expense is that you have to have two tanks, and you have to have space for two tanks. And so there's a little bit more expense. Yeah.
Steve, you don't have a picture here, a heat exchanger? Do you have
the heat exchanger is in here, and I'll show you pictures of the heat exchanger a little later. Basically, the way the heat exchanger works is that there's two pumps. The water from the domestic water is pumped one way, this way, and the water from the solar house, from the water solution is pumped the other way. And so they're pumped past each other through two concentric tubes. And so it's called two heat exchangers. So there's a tube within a tube, and propylene glycols pass one way, and domestic hot water pass the other way, and that heat exchange is in heat exchange in this commercially available appliance. Another advantage of this particular system is this all is hauled out of the factory, and so the amount of sort of plumbing and stuff like that. But the other one that I showed, these are all discrete parts. So this is a lot more, common individual parts we can put together. So this one has been packaged into an appliance. So it's less labor in this second. Yeah.
So in the gas water heater, that's where the water is going to domestic use.
Yeah.
You have that off all day. Does that cool down a bit?
Well, it's on its own set point, and so this natural gas one will gets down below the temperature set point on a conventional natural gas water heater. It'll kick on and boost it back up again. So yeah, it'll turn on.
It looks like that can also happen. You could have the other thing getting very hot, but if you're not drawing the domestic water, then you can't take advantage of it.
That's true. That's true. And part of what makes there's a couple of things that make solar hot water systems really work efficiently. One is you've got a family. You've got a lot of hot water usage. If you only have a couple of people, it's not as good as if you have a family. The second thing is if you're willing to adapt some, so you do a lot of hot water use in the morning, then what you're getting is this water that was hot the night before going through this system. And then this is cold, and so then this can be heated up. So you don't have to do it that way, but you get some additional, better performance if, you slightly tailor your hot water usage. It's not a have to, but you just get better performance. Okay, so how do you size these systems? The design goal is between 50 and 80% of the annual hot water usage. So we're not trying for 100%. We're trying for between 50 and 80. 70 is doing pretty good. Size is based upon the number of people the house can hold, and you're estimating between 15 and 30 gallons per person per day. Get a lower number if you've got highly efficient hot water usage. People are really conscious about using water, and if they're conscious about using hot water, then you're not going to use as much. Higher number for a typical household, particularly if you've got kids. You've got a lot of kids. One of the best systems is a guy and his wife with 3 boys. Just perfect. They're gonna go through some hot water. If you have a couple, then the cost of capital and payback is not as good. And that's one of the difficulties with solar hot water systems, is that they don't scale particularly well. There's a nice size system, and that a couple with 3 children is a great fit. A couple with just 2 people, not so good. Okay, collector area, use about 20 square feet for first 2 people, and then 10 square feet for each additional per people. And then there's rules of thumb on how to do the storage tank sizing, and you get more production if you use a bigger tank, and because you can go over a couple of cloudy days better, and a dual tank is better than a single tank. But space, cost, family size, those kind of overrule those guidelines sometimes. I've done both ways, yeah.
So how does that, sort of rule of thumb gallons per day relate to tank size? When you're saying gallons per day, what's that picture for you? Is that more related to collector size, more related to storage? What's it?
There really are only a couple of different design points. There's really only an 80-gallon and a 120-gallon. Those are really the only 2 sizes the tanks are anyway. Okay, and so you also have a choice between you want a single tank or a dual tank. If you use a 120-gallon tank and a 50-gallon conventional tank as a dual tank system, the wonderful thing about that is you're going to have lots and lots of hot water. So you're never going to run out of hot water. People come to town. We had the University of Washington ski team come stay at our house. 15 kids, and I think we got 8 or 10 of them through the showers, or we never run out of hot water because you just have so much. So much. So that's a consideration. This gallons for the size of the collector, that's important, because if you don't have enough storage for the collectors, what happens? You get a lot of energy, and you get the tanks getting really hot, and then you drain the tank really quickly because people use the water, and then you're back on using conventional source again. So it's important to have the larger the tank size, the better that whole thing is. But there are limitations on the weight of the tank and how much space you got. You must supply at least 50% of the annual use to qualify for the 30% investment tax credit. So there's a 30% investment tax credit for solar hot water systems. It includes the entire system. And then there's an 8% Idaho state deduction. So we can deduct it 20% for the first 3 years, and then 40% for the first year, and 20% for the next year. 40% for the first year, and 20% each of the next 3 years. Yeah.
How does that get proven?
A good question. There is the amount this rule. Oh, it doesn't. What they do instead is that you provide a certificate, either a system certificate in California. Here you just have a collector certificate, or the panels themselves. So you know that you've got certified panels, basically.
That's okay. That doesn't tell me
I've never seen anybody. I did have the Idaho guy ask me to come in and explain solar hot water and how it works, how all the ins and outs of it. And it wasn't like I was being audited. He just said, hey, I've never seen one of these before. Can you explain to me what's going on? And so I went and chit-chatted. Yeah.
So I had the same question. I was wondering if you had to put your utility bills in or somehow prove your 50%.
No, I didn't. But I did get a question from, the Idaho,
The tax people.
the tax people. And just went and talked about told them what I was doing. The same sort of thing happened with the plumbing guy. I mean, you never seen it before, so I sort of had to explain to the plumbing guy and how it worked. The funny thing is in Boise, only the domestic hot water and the hybrid tank is subject to the review and the plumbing certification. They don't, the solar side, they don't, they're not inspecting at all. They're only inspecting the conventional water heater and what goes on past that, the upstream side of it. Now, on my job, interesting, but on my job. And so I have a water heater permit. That's what I do. A water heater permit. Yeah.
So to clarify a little bit, we're only looking at the bottom of the side.
Only pardon?
We're only looking at the bottom of the side.
Yes, that's right. Okay.
Everything else is
Well, and there's potable water on the solar side, so,
some.
yeah, that's one. Okay.
Well, you're here, Steve.
Yeah.
Do you think there's a limit to the size of the storage tank where you're not keeping the water hot enough? Is there obviously you endorse?
Yeah, sure there is. Absolutely.
Is it better to have water as hot as you get, or is it better to have more water that's moderate?
Well, what happens in the hot water side is that the hot water goes to the top, and the cold water stays in the bottom. And so the water supply goes to the bottom of the tank. And so even as you heat the water, the top of the tank gets hot, and the bottom of the tank stays cold. So you get this like lake effect stratification in the tank. And so you don't have to heat the entire tank up to get hot water. All that happens is the top of the tank gets hot, and the bottom of the tank continues to get cold water. It turns into, didn't really answer your question. Is there a limit on size? Sure. I mean, if you got 1,000 gallons or something, it would take forever to get that water hot. But the positive side is that as long as it was well insulated, then it would stay hot for a long, long time. So, you would have relatively high temperature water. You have to boost a little bit. If you have a single tank in 1,000 gallons, then you got a little bit more of a problem, because it means you've got to have a 1,000-gallon tank. You got to keep it at least 120. With a 2-tank thing, the only part that you really have to get to 120 is the second tank, and the first tank just you get it to whatever temperature you can get it to, and then the second tank boosts. Make sense? So to answer your question, the trade is between having, you have a large volume, it takes longer to heat it up, but you can sustain many more cloudy days because you have so much water that's hot. With a smaller tank, it gets hot really quick, but then you use it up really quick and it's gone. So, you have to have sun each day to keep heating up the tank.
What level of insulation do you have in the tank?
These are generally R17, R19, and I meant to do one of the most cost-effective things you can do is put a blanket on the water. Very, very cost-effective, and the blankets are like $30. And, the conventional water heaters are not particularly insulated. And you put a blanket on just your conventional water heater, the return is fantastic. You got to be careful not to close off the top of the gas water. You got to stay away from the top. Electric water, you pretty much cover the whole thing.
The bottom level actually very good.
Yeah, and the bottom. Yeah, you only really do the sides. And you can even double it up. There's a lot of diminishing returns that comes in as you put the second layer on. But you can diminish your hot water usage, You know, if you've got a space that's part of your, you know, house, in the wintertime, it's great. In the summertime, it adds to your air conditioning load, or, you know, whatever you're going to use to cool the house. So, you know, it's kind of best to have really well insulated. But the solar hot water tanks are very well insulated. They're, I think it's R17 or R19, I can't remember which. And a conventional tank, I think it's, I don't know, R5 or R7, something like that. Okay, so solar thermal power. So now we're talking about going to the source and trying to say, okay, we've got this resource. What is the capability of this resource? The resource is the sun. What's it capable of doing? So, you know, a bright, sunny, bluebird day with a panel that's facing the sun. So the sun is at right angles to the panel. In Idaho, you can get 1,000 watts per square meter. You know, a meter is a little bit bigger than a yard, and 1,000 watts is like, you know, well, it's 1,000 watt light bulbs. So, you know, it's enough to light your house. So it's a pretty good amount of. It's also like the hairdryer, but you know. But this is continuous, 1,000 watts per square meter. So that's as good as you're going to do. You don't get any more than that. That's what you get coming in. Okay. A 4x collector is approximately 3 square meters. Okay. So you can get 3 kilowatts of peak input power per collector. So you think of a 3 kilowatt maker, you know, thinking about solar PV systems. A 3 kilowatt array is a pretty good sized array. So that's the input power. It doesn't tell about losses, and we're going to talk about that. That's 3 kilowatts. Now, typically that's for the 2 collectors in the system, so that you're up at 6 kilowatts coming in, which that's a significant amount of power. You know, the heating element on your conventional electric water heater is a 4.2 kilowatt heater, electric element, so it gives you an idea. So this input power is 1.5 times what that 4.2 kilowatt electric heater will do. It's a 240 volt, 4.2 kilowatt electric element inside of electric water. Okay, system efficiency is only 50%. Then we're down to 3 kilowatts, and that's not too bad for system efficiency, total system efficiency. At $8,000 installed cost, it's about $2.67 per installed watt. Well, if you know anything about PV prices, PV system prices are around $4 per installed watt. So the PV system cost is still bigger, but this gap between PV and solar hot water is closing. And I'll talk about a comparison if I'm using PV as a solar hot water heater. And I hate the idea of PV, wonderful electrons. All you're doing is heating water in. You know, we do all kinds of things with electrons. But anyway, that's really neither here nor there. The complexity and the cost, this gap, which used to be much bigger, is you know, I think eventually you're going to use PV, heat water. Not quite yet, but pretty soon, because the PV costs are coming down. And the solar hot water costs, because they're copper and glass and, lots of materials, those costs, there's no cost for one. They're not dropping, or PV costs are dropping. Okay, am I using this at all?
I think we're picking it up through this computer.
Oh, okay.
So I mean,
we're all right?
You sound good, but you don't have to hold
if you
it.
feel like a rock star, keep rocking it.
Okay, so, all right.
If we just lay it on the table here, you think we can do
Well, I don't mind holding it.
I don't think we can move this setup. So
Okay. Okay, so here we have collected types. There are 2 broad types of collectors, flat plate collectors and tube collectors. And these have their own attributes. There's 2 other kinds of collectors that are used, integral storage collectors that are used in places like Hawaii and the Philippines and that sort of thing, and batch collectors also used in really warm climates where you don't have freezing. They're not very useful here. And then there's things to consider is tilt angle and azimuth angle. Tilt angle is just as it sounds. You know, how steep is the roof that you're going to put it on. If you have a very steep angle, then it's better for collecting sun in the wintertime. But, you know, I think sun in December and January in Boise, well, good luck. You know, I mean, there just isn't much sun to collect. Does have the attribute that the snow comes off of it. An azimuth angle is, you know, how far are you off of due south? Are you to the east or to the west of due south? That's what azimuth. Okay, so the net collector energy, how much energy you collect, is a function of how much energy comes in minus how much energy gets lost. And it gets lost thermally. So it gets lost as heat through the various ways. So the solar gain is the net solar flux. And this depends upon the incident angle. So it depends upon where the sun is with respect to the collector. It gets the most when the sun is shining directly on the west side. You get losses with the glass reflection and absorption. And then there's the thermal absorber efficiency. And that's really been worked on. That's really kind of a high-tech part of this because they've had almost black body type of collectors. The material properties of the collectors are really good. They're like 97% of the energy that falls on the collector gets absorbed on these copper plates. It gets transferred to the, to the copper tubes. So that part's really done well. Cooling loss is proportional to the temperature difference. If it's colder outside, you get more loss. There's what's called the emissivity of the absorber. And here again, the technology is very good. Emissivity is the ability or the tendency of a hot object to lose heat by thermal radiation in the infrared. Okay? So it's what makes a fire get hot. So when this plate gets hot, there's thermal energy that comes off of it. And you can reduce the amount of thermal energy that comes off by changing the emissivity of the absorber. And that's again sort of it has to do with the coatings on these absorbers. So they want an absorber that's highly efficient at absorbing energy and really terrible at transmitting infrared. So you get these two wavelengths, and they're doing different things with the two wavelengths. Really kind of cool. The thermal loss goes through the collector envelope, so it goes back up through the glass on the front through the tubes. So you got gains, solar gain, and then you got cooling loss, and the net efficiency is the difference. So here's a typical flat plate collector. I'm going to go to the plot section here. It's a piece of glass, and then this absorber, and then this is highly insulated material. This is the tube that's been brazed onto this collector surface. And they come in different sizes, 6 foot, 4 by 6, 4 by 8, 4 by 10, pretty good size pieces. And this is the efficiency plot. This is the more efficient, and this is the special coating that they put on. And this is a less efficient design. This is simply black paint, and that's how they start out, like just painting stuff black. And I'll go into this term a little bit more. This is basically the temperature difference between the water coming in and the outside temperature. And then this is efficiency. You can see the efficiencies max out here at over 70%. So the collector efficiency can be over 70% efficient at collecting solar energy. A PV panel is a really good PV panel. It's about 19% efficient. Now, of course, with solar hot water, you get hot water. And with a PV system, you get electricity. And so it's kind of apple farming. But you can see if your purpose is to create hot water, and if you want to minimize how much roof area you use, then solar hot water is your choice, because you're going to have a lot of roof area taken up to have the PV panels to be able to produce the same amount of energy as you can with solar hot water. As long as solar hot water is your goal. Okay, evacuated tube collectors. Here's what these guys look like. These are evacuated tubes, and because they're evacuated, they're very good at insulating the hot water. And they have absorbers inside those tubes. There's a header that comes across here. This is where the water runs. And these tubes contain a mixture of water and alcohol, and they form a heat pipe that conducts heat up into a header, and then water flows past that header and gets heated up. There are all kinds of tube designs, all kinds of manufacturers. There's water flowing directly through the tube. There's a heat pipe. Some tubes have a single wall, so it's only one layer of glass. Some of them have 2 layers of glass with evacuated, air evacuated in between them. So they're like a thermos bottle, essentially. So they're really, really good at keeping the hot water hot. And then they can have a flat or a curved absorber plate that's in the collector. And, either be flat or be curved so that it's trying to collect, energy from a bunch of different directions. And you see a whole lot of manufacturers. These guys have been around for quite a while. So these guys, some of these other ones have kind of come and gone. So it's kind of problematic if you have something and want a replacement. I run into that problem. You can't get replacement.
What would you do?
This one here, I think this one's, and this one here, this German company. This German company is funny. Sponsors bobsled races and skeleton races in Germany. They're a big sponsor of that.
I think really good.
Late at night, and you don't have anything to do. All of a sudden, okay, these non-collectors. And here's a flat plate, so they sell both, the flat plate, and then here's the evacuated tubes. Now, the thing about evacuated tubes is that you're only collecting energy in the tube. You're not collecting any energy in the space between. You're not collecting energy in the wall of the tube. So it's only the absorber that's in the middle that's collecting energy. So from a surface area point of view, you see this entire plate is collecting energy in this one. And only the smaller sections in here are collecting energy in that. But these things lose heat, and these things don't lose heat very much. So that's kind of the broad brush comparison. We'll go in and talk a little bit more about those collectors. Here's another one. There's a nice rack here. Here's the header. The water goes in one side, goes in the outside. It doesn't go down here. And these are put at a steep angle. Because these evacuated tubes are really good at keeping heat in, snow doesn't melt up. And so you get snow packed around them. And so it's important to keep them at a pretty good angle. But if we get winters like this one, we don't have this snow. So, okay, this is in Dijon, the Buddhist monastery in the western part, western China, near the Burma border. Was blown away. Went into this monastery, and there's this. This is a particular. This is a tank on top here. It doesn't freeze, and I got the collector below. It's very typical design in China. Here it is from another angle. Just this monastery. Everybody's in robes and chanting. It's like what you'd expect of a Buddhist monastery, and yet there's a solar hot water system on it. So. Okay, this is northern China in the winter time, and this is what happens if you use too much fossil fuel. This place is so brown. This is about 10 degrees outside. I never saw the sun. This is the middle of the day. This picture, and so it's just this industrial pollution because it got so much coal and fog. And man, living in there almost looks like Boise in over there. Okay, here's the solar thermal efficiency. This looks what could happen if everybody used wood smoke. I mean, everybody used the wood stove. Josh and I have a running thing like this. Okay, so here is the solar thermal efficiency chart that I was going to show you before. So this is efficiency. So this is the amount of energy coming in from the sun that you collect and use from the collector side. This is 100%, 70%, and so on. Okay? This is the difference between the water coming into the collector, okay, and the temperature outside. So suppose the bottom of the tank is coming in from the Boise Reservoir at 60 degrees. And the outside temperature is 40 degrees. Okay? So the difference between the inlet, which is 60, and the ambient, which is 40, is 20 degrees. So you're down in here, and the efficiency is very high, because with either any of these collector designs, you're not losing very much temperature, very much to the outside. Now suppose that we've got the tank up at the end of the day, and it's up at 120, okay? And suppose it's 20 degrees outside. So 20-degree day, you manage to get the water up to 120. So it's continuing to circulate. So the water coming into the collector is now 120. So if you look here, that temperature difference is 100 because, 120 inlet temperature and it's 20 degrees outside. So the efficiency has dropped on this one to 50%, to this one 40%. Okay, so this particular line is black pink. And you see that this line where it's a selective surface, this one has got the low emissivity coating on it. This one doesn't give up heat very easily, so it's more efficient at this 100 degrees. So, and here are these evacuated tubes. And you say, well, gee, the evacuated tube is really not very efficient down here, but it's really good out here. Much better. Compared to black paint, it's just way good. Okay, and the reason is twofold. The evacuated tube, in this example, you've got to pass through 2 layers of glass. And so the amount of energy that gets to the absorber is cut because it's absorbed by those 2 layers of glass. So when it's not much difference between the inside and the outside temperature, you can't get maximum efficiency now because you've got to go through 2 layers of glass. The second reason why it seems to be a little efficiency is that this efficiency is per unit of surface area. So if you remember, on the tube collectors, there's all kinds of spaces between the tubes. So this is energy per unit of surface area. And the tube guys probably foul this all the time because they said, well, if you just use the surface area of the tube itself, your efficiency would be much higher. But because the calculation is done per surface area, a lot of those tube collectors are slots between the tubes. And so there's no ability to collect between the slots. And so their efficiency numbers are low for that reason. And so they said, no, it's not right. So, you can change this up and down depending upon how you account for the slots between the tubes. But the basic idea is these tubes are very good if the water coming in is very hot, or you want to produce very hot water, or you're in a really cold climate, where it's minus 40 out, and so the losses going out of it are really important. Then tube collectors really work well. So it's like processed water. If you're running a dairy, you want 160-degree water, you always want really hot water. So tube collectors would be better. If you're, in Saskatchewan, it's cold, it's windy, and, it's that way all winter. You want to make sure the water gets hot. Tube collectors. Boise, well, California, you're up in here anyway. It just doesn't, not that much change, So, anyway, it's kind of application thing. Okay. I'm going to go through this and we'll get a break. Okay, so the tube collector guys like tubes, and the flat collector guys like flat plates. And so, you go to any of these places, they'll tell you about the advantages and this and that. So I'm gonna run through it real quickly. The flat plate is a mature, it's rugged, it's a reliable technology. It's been around for a long, long time, and it's primarily made in the U.S. The evacuated tube, you have high efficiency under extreme conditions. Big temperature differences, high winds, very high at the extreme conditions. Or if you want really hot water. Flat plate panels are heavy, awkward to handle. These are, 120-pound panels. I mean, you can do it. I mean, you just make some more around. You have skilled guys like Josh is. But, if you're up on a 45-degree roof, 30 feet in the air and trying to handle 120 panels, it's not great. Okay, the tubes are lighter, and there are a lot of them, and they're easily replaceable, provided you can still find the tubes from the manufacturer. The flat plate advantage is there aren't any tubes to replace. You don't want to replace anything. Okay, for the flat plate, cosine law directs the amount of light collected, so the amount of energy collected drops as a cosine with the angle that the sun is at. These tube collectors actually are pretty good at collecting energy even in off-angle conditions. They've got better response when the sun is not directly on when they're coming in at a low level. These things look like a skylight when they're flush mounted. The tubes have this high-tech look. They kind of look cool. The slow slides off or melts more easily on a flat plate, although if it's not flat, it will just pile up. The snow can pack in and around the tubes. In fact, in the conditions for this frost, the tubes will frost over. So you get up and, the first thing that the sun has to do is to melt the frost off of the outside of the tubes before the sun can get into the tubes. So the tubes should react, so they'll frost over the tubes. Okay, upper temperature limit is limited by the heat loss with glazing. With the tube, you can reach very high temperatures. And if you've got a large enough storage tank, that's okay. You can't re-radiate at night very well in the tube collector. With a flat plate, if it gets too hot, you can re-radiate the night sky and cool things off. You can't do that with a tube. You've got done some heat at night, what's called vacation mode. Not as sensitive to optimum tilt angle. Now this is the tilt angle, not the azimuth angle. So the tilt. These two dilated tubes it's important to get the tilt angle right. This is best at an optimal seasonal tilt because the conditions you're using them in is if you had an off-grid place and you wanted to have hot water in the wintertime, you didn't really have, you had propane as a backup, then you'd want to mount these with a high tilt angle. Well, you've got to integrate that into the architecture. You may not have a high tilt angle in your roof, and your choice is, well, making a high roof angle where you don't necessarily want one for architectural reasons, or putting up a rack, which, that's really very good. So I like the flat plate for that reason. And then this is simple, less to go along. Had these tubes lose their vacuum, so that's new. Tubes are generally made in China. I think it's probably a little lower cost per BTU, but that's probably debatable. Get two guys and they'll say, well, my system is less expensive. All right, break time. Thank you. Yeah.
Actually, I'm gonna jump in and say a few words before we finish, right? So, thank you for the first half, Steve. And what I wanted to mention is we kind of put this series in topics, so we get the idea that it's kind of discrete, it's solar hot water, or it's solar PV, or it's insulation. But every single topic is a piece of the puzzle as we get to more carbon neutral energy. And one of the things that's happening concurrently with what we can do on our homes is the utilities are integrating renewables more and more onto their grid. And solar hot water is a place where it overlaps really well because water stores energy very well. And Steve mentioned that we might be using photovoltaics to be heating water in the near future. And one of the ways that can work on the utility scale is if you're asking your utility to bring more intermittent renewables onto their system, they need a way to store that power because they've got intermittent power now on their system. And water is a good way to do that. And so there are products coming on the market in the hot water heater area that are larger volume and they can hold heat energy, and they're heat pumps. So they're using electricity to heat the water, and that can come from an increasingly renewable mix on the utility portfolio. And they can do this through a demand response technology, the smart grid technology, where they can operate your appliances for you when they have power available. And so what I'm trying to say here is it's all part of the puzzle, what we put on our roof, what the utilities do. It's all moving us towards a system where we can use less carbon fuel sources, and water is one of those ways that can do that very well. So I just want you to think about that it's not that solar hot water is one equation, what we can put on our roofs is one part of the equation, what the utility can do in terms of intermittent renewables is another, and solar hot water as a battery essentially is a way that they overlap, and we can all participate in a less carbon intense energy system. So I just wanted to kind of get that out there while we're thinking about solar hot water. It's beyond the scope of this class, but it's easy to, something you can look at. You can Google, they're usually Staples is one of the manufacturers that makes a heat pump, water system, high volume system. You can also heat your home with that. It doesn't have to just be what comes out of your shower head. You can have it out to heat your home. So something to think about as we think about systems as a whole and how we can make our homes better. With that, we'll go to break, and bathrooms down the hall. I did pop open the door and repeated that. We've got snacks over here. Kind of got a beefed up snack already this time because I know Power left some snacks from their previous educational event here earlier in the afternoon. So thanks for coming out, and we'll be back in about 10 minutes. How do you spell Staples? S-T-E-F-F-L-E-S. They also make a thermal mass heater system too. It's an electric heater that'll heat a mass, which
It
will
wasn't
heat
just
for a
now,
long
it
time.
was just coming through.
And so if your utility is using an intermittent
But I'll try to hook it up.
generation source, you can turn it on and off, but you'll still have that heat available in your home.
Yeah, so I had this plugged in back here, and it works because
Yet, but you can think of like you have a little chiller reservoir right there.
and then when I plugged it in there, I could hear things, but I realized it's
the United States mostly has heating degrees based on the whole.
Can we
get that
But
yeah, we could do that.
Cooling.
I'll give it a shot.
I haven't seen the verses on here. That's my guess. Use their HVAC and everything.
I'll guess they could 10. I don't think.
I haven't missed it. Usually, I don't. I hardly. He's really busy. I've traded some emails with him.
Okay. Not a long time ago.
Well, maybe we should have that question.
It seems like. Hello.
Yeah.
Hello.
Oh no, it's
Where's the mic here? Hello. Hello.
maybe we could. Try plugging it into this one. That's so weird.
Well, and I wonder, shoot, yeah, I wonder if we lost. Do we still have the webinar? So
Yeah.
how is it? What's this computer for?
So it does the slides and presents the slides like this. So it's a screenshot, and then this one does the camera.
It's weird. It's weird that it was working and then it quit working. It's weird. It seems like it's not this because
There's a natural
Yeah, sorry.
I unplugged it just now.
Yeah.
Yeah, I'm gonna bring it up here.
So I was listening at my desk, and all of a sudden,
Oh yeah, that's probably right when I unplugged it.
I could hear everybody in here. So what do you think?
It's weird because yeah, it looks like it's like the mics are connecting to the stand, but then that's not connecting to the computer.
Yeah.
So that's weird.
Well, look.
So I talked into the computer?
You just can talk.
Okay,
It
all
makes
right.
it for everyone, so like they ask
Okay.
questions, you don't
I had this problem earlier. We had to restart. We restarted both, and I'm not sure which one. Okay, time to get going again. We're a little after 8:15, so we got about 45 minutes left. Okay, so we're getting back together. We've rearranged some of the audio visuals. Hopefully that'll make the audio better for the internet land out there. Steven's taken us through some of the considerations of different types of solar hot water and design considerations, and that was part 1. We're moving on to part 2, so stay tuned for what's new in solar hot water.
Okay, so with your taxes, this is what you add to your taxes, is this certification from the what's called the SRCC, and it's a certification body in Florida, and they certify both individual collectors and complete systems. For the feds, just a simple certification sheet for the particular collector you're using is sufficient for the federal. In some places, I think in Oregon, for systems, you have to have a complete system certification to qualify for what's the one? Energy Trust, I guess, in Oregon. It's they're giving you more money, so you got to go through more hoops. So this is done for every collector, I think, that's out there. There's this huge body of information of all these collectors, and everybody goes through the same place. It's a place in Florida. And I won't go through all the technical details of it, but it's basically an independent testing lab that tests collectors. So the metrics you could use for system performance, you could use gallons of hot water, how many BTUs do you get a day? You could use the tons of CO2 avoided, and I like that. I like avoiding CO2 production. You could use the usable BTUs per year per dollar. That was kind of the calculation you were headed towards. Dollars per year, the current cost of natural gas. We'll do some return on investment kinds of stuff a little later. Dollars per year, the current cost of electricity. Electricity prices are going up slowly, but they are going up, sometimes not so slowly. Natural gas prices are actually going down. The technological improvements, if you want to call them that, of fracking are driving the cost of both oil and natural gas down, and so it's a real headwind for any kind of renewable energy, particularly thermal renewable energy. So economically, it's going the wrong way. There's a life cycle cost of energy. You could do that kind of calculation. How much energy did it take to produce all this stuff? And it's not as good as, say, PV, where PV, it's about 2 years worth of energy production to offset the energy cost of producing photoelectric. Where here now we're doing copper and glass and bulk materials and pumps and stuff like that. So I don't know the cost of the energy involved in putting all these things together, but I'm sure it's not as good as PV. And then there's the external environmental cost of fossil fuel. So, how do you make the trade? You don't. I mean, you just do it, you believe it. Okay, so collector tilt angle. So this is for a south-facing collector. So any kind of collector, and now we're just measuring how much energy we get from the sun, depending upon what the tilt angle of the roof is. Okay, so you can have a flat roof, and that is the blue line. That's this line here. That's a flat roof. You could have a 90-degree wall. You could mount, say, a tube collector on a 90-degree wall, and that would be this orange line here. Okay. Difference between the two seasons is the amount of clouds you get between the spring and the fall. This data comes from PV watts, which is a very useful way of understanding how much energy you get from the sun. And you see various other lines at various degrees. A typical roof, is usually between 15 and 30. 45-degree roof is a pretty steep roof. And, I have seen steeper roofs. I've got a picture of one. But what I really want to point out here is that most of the energy production occurs in the summer months anyway. So if you're looking at the total energy production, it's kind of from February through November. That's really the heart of your ability to produce a lot of energy. Down here, you can get good improvements if you have the right orientation, but you're not dealing with very much energy to begin with, and that's because you just don't have very much. You don't have very many sunny days. And so you're attempting to gain energy when there isn't very much to begin with. So yeah, you could double the amount of energy you could get, but in terms of the total production of energy over the entire year, it's really relatively small. So basically, you end up mounting these collectors at whatever roof angle you've got, or you build a rack. And I would argue that you shouldn't build a rack because they're ugly. But that's just a personal preference. So here are some that are integrated pretty nicely with the roof. Here's the photo, the PV that runs the pump in this particular one. So this isn't, this is independent of the grid. So if the grid goes down for some reason, you don't have a pump that isn't pumping and collectors that are then getting hot. And that's a pretty good solution because the PV is, if it's sunny enough for the PV, it's sunny enough for the solar hot water. So those go together pretty well.
So is the pump part of the collector, or is there storage?
It's down below. The pump's down below, but the power to run the pump comes from the PV panel.
So there's no storage device in there?
Oh yeah, there's storage device and all the other things. It's just how the pump is powered. Instead of being connected to the grid, you're connected to a solar panel, and because of that, then you're independent of the grid in terms of the performance of the system because the pump is run by the PV panel. Here's a great house for either PV or solar hot water. I think you know this house if you've ever driven in the North End. It's just, you look at this house, you go, wow, that's a great one. Looks like they got satellite TV. Here's it's a house not very far away from it. Here's an example of a roof that really is steep enough to do the high angle stuff. You could put evacuated tubes or something up here. This is this is the steepest roof I've seen. It's more than, I think it's probably more than 45 degrees. It's an incredibly steep roof. But architecturally, would you do that all the time? No, probably not. Here's a sort of illustrative of sort of the compromises between aesthetics and house design. I mean, the house was designed before the panels, and so you have this triangular shape, and you're putting squares on it. It looks okay. It doesn't, it's probably not ideal aesthetically, but they got them in there, and it's a pretty darn steep angle. That's a flat panel on that one. Here's multiple panels. Here's a relatively high angle with evacuated tubes. So you don't have to have a steep roof. You don't really lose that much to have them flat. You lose more due to snow collection because the snow builds up on them, and until the snow slides off, if they're dead flat or if they're like 10 degrees, the bigger problem is once there's snow on them and they're up high, you're not going to go off and go rake them off, and so you don't have any collection ability until the snow's gone. So that could be weeks sometimes in Boise. But as I said before, if you just don't expect to gain much energy between about Thanksgiving and kind of the middle of February, that's probably the certainly middle of December to the middle of February. Just kind of write that off. You get some, you'll get the water heat up to be 80, 90 degrees, but it won't be great unless you're particularly oriented. So. Okay, here's collector azimuth angle, and once again you can see that azimuth angle is very important in the wintertime. But doesn't make much difference in the summertime. The amount by percentage of total solar gain you get, even if you're east and west facing, really isn't very much. And it's better if you're flatter because then you're just kind of seeing the sun overhead. So it's a big deal if you're really trying to gain energy in the winter months. But it's better. You're going to use a hybrid system anyway. So. There just isn't that much penalty for being off. So my take on that is you have other architectural or mechanical or other reasons to define what the tilt of the collectors are, and don't spend a lot of energy on racks or trying to optimize them. That would be my take. Here's a roof that's facing east, and you can see that there'd be a place to put solar hot water on this roof, and there'd be shading on either one of those two roofs. There are some places where it just doesn't make any sense. This is Hong Kong, and so where do you put the collectors? There's just the density of people is so high that you couldn't, it's just not going to work unless you maybe do vertical collectors on the sides of the buildings.
Yeah.
Well, the interesting thing about Hong Kong is I don't think you can see it here, but all the utilities are on the outside of the buildings. All the sewage and the plumbing and the electricity and all that sort of stuff that's typically in the inside here. It's all on the outside. And they figure they don't care what the outside looks like. They live in the inside. They look out, and the inside space is too valuable. So all the utility stuff is on the outside of the building. It's all nice and neat and stuff, but you can see that they felt like this is the most important use of the rooftop, is put a garden. And here you see this bamboo scaffolding, which really just blows you away. You have many, many, many stories, 20, 30, 40 stories of bamboo scaffolding. Okay, solar storage tanks. We've already talked mostly about this. Single tanks, good when space is limited. Rely on temperature stratification. The top of the tank gets hot, the bottom of the tank is cold because it's got cold water in it. You put the heating element at the top of the tank, so you're not constantly trying to heat the cold water at the bottom of the tank. The water from the city comes in at the bottom of the tank. The top of the tank is hot, and if it needs to be boosted, it's boosted by a heating element at the top of the tank. And you're relying on the stratification of the water. And, you can use it electric or natural gas. Single tank solutions are almost always electric. Internal or external heat exchanger, so you can do it either way. Dual tank systems are more efficient, have more energy storage, they're more expensive, take up more space. You can also make use of existing water meters, so you're really not buying, you're really buying just a storage tank. Okay. So variety manufacturer tank, some of them are familiar. Ream is a familiar name of tanks anyway. This particular one has got the coil around the bottom, so that's a heat exchanger built into the tank. Here it's heat exchangers which are inside the tank rather than around the outside. And for a while in California, you couldn't use these because this is what's called a single wall. There's only one wall between this tank and the potable water. So there was concern that if people put in non-food grade glycol, if they put in ethylene glycol, which is poisonous, instead of propylene glycol, ethylene's much cheaper, and you can get it, because you can put it in your car radiator, but it's poisonous. So if they use that and there's a leak in this thing, they were concerned that it would pollute this water supply. But with propylene glycol, and the fact that this pressure in this tank is much higher than the pressure in the solar hot water system, usually, these have now been approved. I think approved in Oregon. This particular system, you have a heating unit here. This is where the solar hot water comes in. And this is a takeoff for space heating. So you have domestic hot water in the tank. This coil heats the water in the bottom. This coil takes hot water off to do radiant cores. Yeah.
Is there a particular reason why they got that winding separated on the down at the bottom?
Oh, I don't know. I don't know what this little drawing is.
Yeah.
Yeah, I don't know what that is. Maybe that's let's see. There's a clean out report here. Maybe they have some. I really don't know. I've never even noticed it, to tell you the truth. Okay, this is German company. Here's another A.O. Smith. This is simply a solar hot water tank. There's no heat exchanger in it. You see the four. There's domestic hot water, domestic cold in, domestic hot out, and then hot water in and out from an external heat exchanger. So there's no coils in this one. Okay, the types of heat exchangers, you have an internal or external coil, you can have a tube and shell, you have a flat plate, integral with a collector, and some AHJs required dual wall heat exchangers, and that's all the ones I've used, where you have a tank and then the tubes are wrapped around the outside of the tank, or if you have a tube and tube, there's actually an airspace between the two tubes. So if there would be a leak in one of the tubes, it doesn't go into the other tube. There's actually an airspace. Okay, the differential controller, it just turns the solar loop on and off. That's its function in life. So sun's out, collectors get hot, turns it on, yeah.
Going back to the code requirements around segregation of the heat exchanger.
Yeah.
Is there a sensor that could tell if the water became contaminated with the glycol solution, and you could just, an alarm go off or something like that?
I suppose. I haven't heard of one commercially, but
Your skin will know it's pretty quick. You'll be out of hot water.
You might taste it.
Well, it's very slick. And then you'll run out of hot water too, because once your hot water system drains.
So, but I mean, is there a risk of being poisoned?
if it's propylene glycol is used in all kinds of food industry, so.
McDonald's 15% of pink juice stuff they were talking about. So they take all the crappy meat and put it in a dryer with propylene glycol and make it edible. They use propylene glycol to kill the bacteria and everything else. So yes, it is very, very bad for you, but somehow we ingest it on a regular basis.
And
There's all kinds of uses for propylene glycol, some of which I won't go into.
I'll leave my conspiracy theory.
Yeah. Okay.
It is cancer rates. I'll just leave it.
Yeah, cancer rates. Okay, so to avoid that, dual wall. You have two separate walls, and so if you get a leak in one, it doesn't go into the other. Okay, differential controller, we talked about that. There's an upper tank temperature limit. You can take various actions depending on what happens to that upper tank temperature limit. You can cause it to dump the hot water, you can cause it to divert it to some other place. There's vacation mode, and what that does is at night, if the tank temperature reaches a certain temperature, then you recirculate the water up into the collector, and the collector acts as a radiator at that point and actually cools the water down. That works this time of year. It doesn't work so well in July because it's just hotter, and it just doesn't cool down enough. And a dump valve relay, which I've installed in most of the systems. And there's all kinds of ways of measuring temperature and BTUs and getting diagnostics, and you can go crazy with the wireless stuff that's there. Yeah.
Do any of the solar thermal systems have a mixing valve on the outlet of the tanks so that you add cool water to it to make sure you back on the same temperature?
That's essentially what happens with the dump valve. What you're doing is you're dumping the hot water, and cold water comes in to replace it from the city. And so, as you take this, you take hot water from the tank, you run it through a mixing valve, so it's only 120. So you don't want to dump really hot water. And you take that into a rain barrel. So you got 120-degree water, which is safe, and that goes into a rain barrel. And then water from the city goes to the bottom of the tank to replace the water you're using, and that cools the tank.
If you don't want to dump the water, can you get the water that's going out to your fixtures lower than the tank temperature?
Anybody?
I have a very simple solution. I moved up here from southeast Idaho, and what I did with mine is I put in a field a couple of feet in the ground and did a blowout like a sprinkler system, and I heated my garden. So I actually increased my growing season by 6 weeks on either side of winter because it produced way more temperature than I needed to either heat my house or do anything I could do. I could shower nonstop with what I could produce out of the panels during the day and the energy heating. But I did it like a geothermal loop because it's 55-degree ground temperature, and I did mine in a different system. So I used the Beastman panels that I showed here, and I worked with a German engineer when the stuff was kind of new 10 years ago, and elevated my pressure in mine to 50 pounds of pressure, and my glycol loop could stay static at 338 degrees before I produced steam. So I could hit almost a 100-degree day before I ever ran into the problem of overheating. And if I did overheat, all I did is ran it out, and it ran the loops through the ground. It kept the frost off the ground, and all my stuff started to grow earlier in the spring, and I could grow later in the year before I had to harvest certain things. And it was just and that way I wasn't wasting any water, I wasn't having to mix anything, I wasn't going to do anything, I just had some extra tubing that I buried essentially in the ground on square footage. And it's very easy to calculate square footage on BTU output of units for what you need to do. It can be done on, a lot of small lots on small homes and garden spaces and things like that.
So what triggers that bypass?
Same thing.
Just to,
So if you get to the point where your tank has all the capacity, and then mine was done by pressure. So because as the temperature heats, the pressure rises. So if it got to a certain pressure, I would kick on, and it would actually bypass. It would leave what was in the tank, and then it would by pressure would go out and it would run through the loops, and I would pull it back at 60 degrees.
So you were running the solar out.
Yeah.
You were running the solar part. Yeah.
I just basically had it.
So you weren't dumping any water in that.
I wasn't dumping any water. I just had an expanded loop strictly for a solar dump. That's all it was.
Yeah. And there's a variation on that one, which Rural Power and Design likes. And they just have a radiator, and they go through a radiator that's right on the roof, right next to the panel. And so they just take a portion. When it gets a certain temperature, then they run the hot water through the radiator, and it radiates out. I don't know if that answered your question, though. Okay. I like the dump valve because if you're on vacation, you're going to want to water your garden anyway. And so it goes into a rain barrel, then it just, goes out in the garden of the drip system. So it's water, it's not wasted water. It's just water you're going to use anyway.
And it's only happening in the summertime.
It's only happening in the summertime when it's hot anyway. So that's where the one problem I did run into was when people ran it through an uninsulated wall and made a vertical loop in it. And then it froze. So you've got to make sure that the loop is going to drain. It's got to be because it's going into the rain barrel, so it's got to be a drain. Either that or you got to drain it. It's better to have it so it's a gravity drain. It does that automatic. Okay.
Self-regulating thing for the garden, because on the days that it's the hottest, that's when you have to dump the stuff, and that's when you need more water in the garden.
Yeah, it's a nice solution. It's not bad. Okay, so this is this appliance that I was talking about. So these are the two pumps, and this loop here is a tube inside of a tube, and so this is the heat exchanger. This comes with a couple of temperature gauges. It's got a flow meter, and one of these loops goes to the water tank. That's the potable water loop, and the other pump goes to the collector. So it does require two pumps, but it's it's a nice factory, built system, and so it's arguably more dependable than something that you would build together from a plumber. I did have a problem. One of these joints in here, there was an ever so slow leak because were Loctiting these fittings. And they didn't Loctite the fitting, and the water slowly evaporated over, I think it was 5 years, and the pressure slowly dropped, and the guy called up and says, hey, I don't have any hot water. I went on, and well, it's because there's no pressure, so the pump doesn't work. And so I had to go fix that. Okay, I've lost my clicker. There we go. Okay. Solar hot water is an investment. So the characteristics of it is an investment. It's an immediate switch to a renewable energy source. When you get it, take the first shower and you go, okay, I've made the transition. I'm on to renewable energy. That's a nice feeling. Sustainable, local. I mean, it's local because it's right there. It's yours. Low carbon solar energy source. It seeks to minimize the environmental cost of energy, but it takes energy to build all this stuff. A homeowner controls the asset, so for good or bad. It's an effective hedge against the future cost of energy. But if natural gas prices go down, then it's less effective as a hedge to the future cost of energy. For electricity, it looks like it's pretty good. Annual rate of return may grow over time. So the avoided cost of energy gets better and better the longer you own it. So it's the return on it continues to rise. The effective income stream is tax-free. You're not paying tax on the energy that comes in. It's a long-term investment. It takes a while to pay off. Energy is essentially free after a payback time, and in this area, it's about 10 years. So this is the incentives. We talked about that already. Here's our return on investment. This one's a little better than 10 years. This is it's a little better if you're offsetting electrical energy. It's really good if you're offsetting propane. I mean, if you're out where you're using propane to heat, then it's really good. It's much better than heating with wood. But the propane that works, but natural gas, natural gas prices are really coming down. This is space heating. So now we're transitioning for the last little bit of this to talk about space heating. So we've done a number of these systems, and the catch with space heating is that you want the heat when you have the least sun. So that is the fundamental drawback to using these for space heating, particularly in a cold climate. You just don't have the sun, particularly in Boise, because of the inversion. If you had a beautiful, bright, sunny day, and if you were in Sun Valley, then it makes much more sense because you get a lot of reflection off the snow. There isn't the inversion. You get a pretty good solar resource even in the wintertime there. In Boise, it just is overcast or it inverts, so it's tough that way. Anyway, this was a space heating system, and the way this was set up was with 4 4x10 collectors and 2 120-gallon hot water storage tanks, and this packaged system from Heliodyne, and 4,500 watt, 240 volt heating elements in here. And the way heat was transferred to the house, it had a conventional stack, forced air stack, but there was no boiler or there was no furnace. So in place of the furnace, water went through a coil that's usually used as a space where you usually have an air conditioner in the vertical stack. And so hot water goes through this coil and goes into the hot air that then goes into the house. So it's a forced air system, but it doesn't use any natural gas. The backup mode is electricity, and it relies both on solar hot water coming from these collectors and electricity for a backup. And it also produces domestic hot water, again through a mixing valve, and so it's both domestic hot water and a space heat unit. And the place where this really works well is from about February through May and through